So last talk before afternoon tea, that's a good thing I guess. So when I put the schedule together for this mini-conf, the previous talk and this talk, I couldn't really find a spot for them, and then I realised they were both on embedding. So our presenter now is Alistair De Silva, who is one of the founders of the Make Hack Void hackerspace here in Canberra. He's going to be talking about designing an efficient runtime library for AVR microcontrollers. Please make him welcome.
Thanks, Chris. As he said, I'm Alistair De Silva. I founded, or I'm one of the co-founders of the Make Hack Void hackerspace here in Canberra. I'm going to be talking today about one of our projects at Make Hack Void, which is MHVlib, which is an alternate runtime for AVR microcontrollers. Typically, people run Arduino on these, and if they don't like that, then they go down to bare metal. I'm trying to do something which gives you almost bare metal performance, but gives you a nice user interface so you don't have to rack your brains trying to remember register names. I did not press that button hard enough. MHVlib is basically a runtime library for the AVR microcontrollers. It'll run on Arduino boards as well as naked microcontrollers, so you can embed them in projects and things like that. We've got people at the space using them to fly aeroplanes and quadcopters. You'll probably hear a talk from Tridge later about running these things in the Outback Challenge. This particular library is basically a wrapper around AVR libc, which is the C runtime library that's provided for the AVR microcontrollers. Also sits on top of the GCC and GNU binutils toolchains. We actually maintain our own distribution of that as well to make sure that they're all up to date, because in the Windows world, the last version of GCC for the AVRs was version 4.5, which is ancient. But our distribution's available for Linux and OS X as well. The library that we use or we provide is BSD licensed. However, there's a few wrappers around things which are GPL'd, and so we've actually got a separate project that contains all the GPL components, and of course all of our wrappers are GPL'd as well. So one of the things about the AVR microcontroller is it's a very, very different animal from the type of machine you're used to programming. Well, probably used to programming. The first thing is it's a Harvard architecture machine, so your RAM and your your data and your instructions are in totally separate address spaces. Your program code is read-only, so you can't do nifty things like you can abuse in the PC world and write code into memory and then go off and execute it. Your libraries are statically linked. We don't really have a runtime environment on the microcontroller that can go off and do dynamic linking of libraries. And we're extremely limited in the amount of space that we have available on the microcontroller. So the typical microcontroller that people use is the Atmega 328, and that's only got 32 kilobytes of RAM, 32 kilobytes of flash memory, 2 kilobytes of RAM, and 1 kilobyte of EEPROM for persistent storage. So the first thing in MHVlib is that I'm using this as an exercise to learn about C++. I've come from a Java background. I program in C and Perl at work. And the Arduino was my first touch on C++. I did get kind of antsy about the lack of control that API provided, so we set out to build something a bit richer and more efficient. However, because it's a learning exercise for me, as I learn new things, I need to go off and implement them, and some of those implementations require that I break the API. So one of the things that we really need to do when we break the API is to try and play nice to the users. So we only break the API on major version releases. All of the breakages are well documented, and where possible we try to leave wrappers in place so that old code still continues to work. With some of the refactoring that isn't always possible, but at least we group everything into a big bundle of breakages before we punish the users with all of those. So the first optimization that we did in MHVlib is to make sure that we use the appropriate data types for the data we're storing. Developers often just go to their favourite data type. In our office, people tend to go to longs. In Arduino land, they go to ints, which are 16-bit integers on this platform. But as you can see, there is a performance penalty for operating on 16-bit integers. So if you've got a value that is going to be within the scope of an 8-bit int, so for example, if you're going to be doing a loop from 0 to 128, then you could just use an 8-bit integer for that loop, and your code will function perfectly without any performance penalties. So I mentioned earlier that this machine is a Harvard architecture machine. So we've got all our program code that's sitting there in Flash. Any variables that you declare will be both in Flash for the initial value and in RAM for its runtime value. So if you go and declare an int and you're only going to be using out of context, then it really doesn't need to be sitting in RAM. And because you've got so little of it, you really want to conserve that for other usages. So in AVR libc, there's a couple of macros. One is progmem and the other is pstir. And what they do is they take your data and they store them only in flash memory. That conserves your memory for later usage. In C++, you have to make a function call to get that value out of flash memory. Fortunately, it's all inline, so it's not disastrous. But a new feature that's been added in GCC 4.7 is named address spaces. It's only available in C at the moment. I'm really hoping they implement something similar for C++. But it basically means you can take your data that you've stashed away in flash memory and treat it just like any other variable, which is kind of cute. It makes your code a lot more readable. So, I already spoke about that. So one of the things that I did fairly early on was look into what features were available in the compiler and linker to try and cut down the amount of code that ends up being written to the microcontroller. So there's this rather nifty function in GCC called function sections. And what it does is in the ELF file that it generates, it creates numerous sections in there. And typically all your functions get put into a single section. If you specify function sections, every function that you write ends up in its own section. And then when the linker comes along, it can say, well, no one's actually referenced this section, so I can discard the whole thing. And the end result is you get to save a bit of your flash memory usage by discarding those. You can also remove some unused code in the compiler. So this was a technique that I learned a few months ago, and it resulted in a very, very major rewrite of the library. So basically, it comes down to this. A branch that can be evaluated at compile time, the compiler will simply discard the unused bit of the code. So if you can pass the condition of your branch in as a constant, then you can cut down the amount of code usage. Now, the thing that I learned is that template parameters are constant at compile time. So if you've got a class and you need to pass some initializers to its constructor and they're never actually going to change, then you can pass them in as template parameters instead, which makes life a little bit hairier when you're trying to debug it, but it means that the compiler can go and discard huge swathes of code which will otherwise be unused. There is a problem there with templates, which is that templates cause code duplication. The way we work around this in MHVlib is we take all the common code in the class which isn't really dependent on any of the template parameters. We loft it up into the parent class. That way we only have code duplication on the bits where code duplication is actually required because it's dependent on those template parameters. So this is an example of how we would do that. So we've got the common parent class up there at the top, which has some method in it which does something with a register. And we've got our foo class, which is going to take a template parameter in. And you can see that we're not only operating on that template parameter within our method, but I actually missed a method declaration in there. Whoops. Teaches me for writing code just before the presentation. But you can see that we can then also call the common code in the parent class, and all the different invocations of our foo class with different template parameters won't have any code duplication. MHVlib recently has taken another turn, which is that typically embedded programs tend to be very linear. You go off, do something, toggle a line high, sleep for a bit, toggle the line low, and so forth. There's basically a single thread of execution. But the problem is that those sleep for a bits tend to be busy loops. And when the microcontroller is doing a busy loop, it can't do anything else except maybe handle an interrupt. So by restructuring your code to be event-driven, and that basically is implemented in MHVlib by hooking various interrupts, it allows you to put the microcontroller to sleep. That lets you save battery life and the planet, if you're powered off mains, I guess. And it makes the main loop very simple. In a lot of the MHVlib tutorials, the main loop is decomposed to the point of check if there's anything that needs to be done and go to sleep. What will happen is if there's an event that the program needs to handle, for example, waiting for a timer event or waiting for a button press, the microcontroller will wake up at that point, go back to the top of the loop, handle the events and go back to sleep. So, efficiency is not just for the computers. Programmers should be efficient as well. Now, some of the things that I'm stating here are probably a bit contentious for some people. We've had a few debates in the office about it. But take what you will from it and feel free to argue with me offline for the rest. So, that slide is incorrectly titled. I want to encourage code reuse, not avoid it. As I said before, factor all your common functions into a parent class and keep just the minimal implementation of what's required in the low-level class. So for example, we've got a class called device_tx, and that has various methods on it which format up strings and buffers and numbers and dump them out to some magical device that can represent this data to the user. It takes this by dumping it all into a ring buffer on the back end and they have callbacks for freeing them when they're dealt with. But what that means is that when you go and implement a driver for a new LED matrix display, you don't have to go and write all this code for handling how to display characters on the screen. There's already generic code there in place. As long as you extend device TX or one of the display classes, such as a monochrome display class, then you've already got code in there to handle what you need to do. So your effort in terms of writing a display driver becomes a case of, well, how do I get data from the constructs within MHVlib and push it out to my device? One thing I'm a really big fan of is code documentation. I'm trying really, really hard to get my workmates to agree, with poor success, unfortunately. But MHVlib is fully documented using Doxygen. Now, there's a couple of nice things about documenting your code using a standard like Doxygen or PerlDoc or JavaDoc, which is that you can run and generate a PDF file or HTML that describes your code and all the methods that are available within it, which is really nice for people who are actually trying to use it because they don't have to keep jumping back to the code to see what the interfaces are. I tend to use code Doxygen for not just documenting the code to the user, but also for myself. I actually write the documentation first, and I use it as a way to keep myself on track and make sure that I'm not pushing more things into that function than it really should have. It's basically a case of trying to contain scope creep at a functional level rather than just at a project level. It also is really useful when you come back in 6 months' time and go, what the hell was I thinking? And finally, when you're trying to debug the code, you can read what you originally intended the function to do and confirm that the behaviour of the code itself actually aligns with that intent. One problem that I've seen, well, actually, where's that PHP guy, is having generic names in libraries. So obviously when you're writing code and you've included headers from 2 different libraries and they've got the same function declared in it, it's going to barf at you at that point. But what happens if you haven't included those headers? The linker is going to go and simply grab the first symbol it finds with that name and link it in, even though the actual internal implementation of it may be completely different. So back in the PHP case, I think there was something weird with XML and MySQL or something like that, and depending on which order you brought in your plugins into PHP, you would get sporadic crashes. But anyway, other story. So the way I had originally worked around this problem was I was prefixing all of my function calls with MHV underscore, and of course all my class names are also called MHV something, which gave me kind of like namespaces, but not namespaces. And then I learned that C++ actually does have namespaces, which turned out a lot nicer. The code's a lot more readable as a result. I'm fairly adamant that any methods and functions need to be kept simple. If a function starts getting too hard to understand internally, it's going to be an absolute nightmare to debug. It also means that when your users go to try and use that function, it's not quite clear what the end effect of that call is going to be. If it ends up doing something but also has weird side effects and people are trying to call it because of those weird side effects, well, perhaps they should actually be 2 separate functions. One anti-pattern that I've seen in use in our office is basically what people like to call utility classes, which tend to end up just being a bucket for any old junk that they want to write. So in MHVlib, we basically have a philosophy that says, well, if there's something in a class, it should really pertain to that class, and if not, well, it probably belongs somewhere else. What that means is that if you go and look at your display class, it's only really going to have stuff about putting pixels on the screen. All the stuff about string manipulation is going to be in another class like device TX. It looks like I'm running quite tight. Okay, cool. I've seen a few other problems in code that I've been porting to MHVlib. And most of these come down to the fact that people have made their variables too broad in scope, and they've ended up with information leaking from one loop to another, or having the context being a bit screwed up because they haven't reinitialized it when they switch contexts. So what I suggest to people is that when you're writing your code, restrict your variables to the tightest scope possible. So that means your iterators should really be declared within the for declaration. Don't reuse your iterator later. And of course, going hand in hand with that is naming your variables appropriately. Now, this has caused some contention in our office. I've been pushing for everything to be named with the same name. Some people say, well, it's okay to name your iterators okay, but as like a single I or something like that. But what I've found is that a number of bugs in our code have been because people have mixed up the context of that iterator, and they've used it as an index into a different array than what it's actually looping over. So of course you get buffer overruns and you start accessing uninitialized memory, and then your program crashes and it becomes painful to figure out what's gone on. So there was one final optimization, syntactical optimization we've done in MHVlib. So one of the features in C++11, which are the later versions of GCC support, is scoped enums. And the way you declare those is, instead of just going enum blah, you go enum class blah. And what that lets you do is it gives you very strict typing on the enum. You can declare the underlying base type that the enum uses. You can declare your own operators on the enum. And most importantly, all your enum values are now namespaced based on the name of the enum itself. So if you've got an enum called color, then you can reference or you can disambiguate it in your code by going color : green. So if you've got a color enum and a RGB enum, then you can differentiate the two like that. So that's pretty much what I've learned from refactoring MHVlib over the last year. So if there's any questions, I can take them now.
Yeah, I've got time for, say, one question. We've got one. Okay.
So what's how would you decide that you should use MHV rather than the Arduino library?
Okay, I recommend that people who are actually experienced developers go towards MHVlib. Let's put aside the whole IDE argument because that's a completely different discussion. But just looking purely at the runtime, MHVlib provides a lot more control to the developer. So you have control over buffers, fine-grained control over the hardware and what it's doing. You can shut down peripherals that you're not using. And of course, with the event-driven model, you can put the machine to sleep as well. So yeah, if you're an experienced developer and want to get your hands dirty with tight control of the machine, go with MHVlib. It also saves you memory, program space, and clock cycles. So if efficiency is important, then MHVlib's also good.
So everyone, please thank Alistair for his talk.
Thank you.
It's afternoon tea time now.